Hello and welcome to this clip looking at an NMR Levelled Response question which includes a D2O consideration. It tells us a scientist is researching compounds that might be suitable as fuel additives, and one of the compounds gives the analytical results on the screen. So let's quickly look at what each piece of information gives us. We can use the elemental analysis by mass to not only work out which elements are present, but also the empirical formula. The molecular ion peak on the mass spectrum. The MZ value tells us the MR of the compound. So those two things together will allow us to work out the molecular formula. The hydrogen NMR spectrum gives us the hydrogen environments, but we need to be aware of the fact it's in D2O, which means that any OH or NH peaks might be missing. There won't be NH peaks in this particular compound because you can see from the elemental analysis by mass there's no nitrogen. So that must mean that the two hydrogen environments that would appear when you run the spectrum without D2O both would have OH in them. So let's start by looking at the empirical formula. So you divide the percentage by the relative atomic mass of each element, which gives you this ratio, which is not a whole number ratio. To turn it into one, you divide everything by the smallest, that being 2.2725, which gives us an empirical formula of C2H4O. So using the empirical formula plus the MR that we obtained from the molecular ion peak of the mass spectrum, you can see that 44 grams per mole, which is C2H4O, goes into 132 3 times. So therefore the actual molecular formula is C6H12O3. So when you do an analysis of an NMR spectrum, I'd recommend labeling the peaks so you can refer to them in the analysis. Now you can write it out the analysis as sentences if you wish, but it's much better and much easier, I think, to maybe do it as a table, which allows you to park the information and not get confused or trip over your ideas. So we have a peak column, we have a chemical shift value column, and we have the hydrogen environments that refers to. This is read off the scale at the bottom. This is obtained from the data sheet. So all of this technically is really handed to you. You're just organizing it in a certain way here. So looking at the peaks closely, I'll do the peak A analysis for you. The doublet comes from the fact it's split into two. That means applying the n+1 rule, there is one adjacent hydrogen. Combined with the fact that the relative peak area is 3, that's the number 3 printed next to the peak, that gives us H3CCH. That H I've highlighted now is the hydrogen that's next door, and the pink hydrogens are the hydrogens that are responsible for the RPA. So going from this point here to this point here is where you pick up the marks. So this part of the table is where the marks are actually awarded. Now you'll see that there are two peaks down here. We said already that they are OH peaks. So looking at the data sheet, the one at 11 is going to be the carboxylic acid, and the one at 3.6 could be OH on its own, like an alcohol. If you look at the data sheet, you'll see that the OH peak can actually sit anywhere. That's why we do the D2O shake in the first place. So those two peaks there are highlighted in pink because they're the two that we talked about earlier. So we have to use this information to suggest a structure with a compound. Suggest means we need to do a bit of deduction, and there's some flexibility in the actual structures we could actually get away with. So looking at the hydrogen environments, you can see that there's 4 in total, 2 of which are HCr. Looking at the RPAs, adding them all up gives us 10 hydrogen atoms, but we know that there's 12 in the molecular formula, so we have 2 spare. That would account for the 2 environments at the bottom that we don't have much information about, apart from what we were told. So now what we do is start to pull it all together. Now in actual fact there's 4 different structures that could account for this splitting pattern. These are not exhaustive, there may be others. The actual mark scheme on this question is quite flexible, which allows you to sort of come at it in different ways, provided you're meeting all of the criteria for C6H12O3 plus those splitting patterns that the information in the question gives us. That means these 4 structures are accepted. Okay, hopefully this has been a useful look at quite an applied NMR question. Until next time, thanks for listening and see you soon.